and welcome. Hopefully you will find this presentation on SOLIDWORKS Simulation Premium valuable. So what we're going to cover today, again talking about the dynamic and nonlinear capabilities in Simulation Premium, is first a brief segment on why simulation might be important. I'm sure that some of you, of course, have used the simulation tools inside SOLIDWORKS before, but some of you may have not. Then we'll go into a little bit of a deeper discussion in what nonlinear means, and what is nonlinear versus linear, and what dynamic means, what is dynamic versus its alternative, static. And we'll look at a couple situations when you would need to use these types of analysis and what they really do for you, what extra information you can get out of the software by taking these factors into account. So if you aren't currently using SOLIDWORKS simulation, you hopefully are at least aware that this is the fully integrated analysis tool inside SOLIDWORKS, where you'll be able to simulate the solid models that you've created under a variety of conditions, typically some sort of load like a force or gravity or something like that, typically to evaluate either the stress in the material, whether it's going to yield or break, or possibly some other factors like thermal properties, whether a part is going to overheat, or maybe if it's going to sustain a certain number of loading cycles. Of course, the benefit for these tools is being able to predict whether or not the products you're designing are going to meet the requirements that you have, if they're going to exceed a certain level of stress or a certain factor of safety. But of course, in addition to that, we are going to be able to optimize the design of the products that we're working on to not just meet the requirements, but to also be as good of a product as we can make it. Lighter product, cheaper to manufacture, more aesthetically pleasing, whatever your requirements are. And of course, by having the simulation tools integrated into SOLIDWORKS, it's going to be the fastest way to try out different design options and do a lot of what-if scenarios in order to figure out what really is the best design. And of course, by having it inside the software, it's going to make it easier to learn, a shallower learning curve. It's going to make it the easiest to use compared to any other simulation tools that might be out there. And in addition to that, it means that you have a one-source solution for all of the support, consulting, training, and that's us, Hawkridge Systems. So if you have any familiarity at all with simulation inside SOLIDWORKS, you may be familiar, for example, with something called SimExpress, which is inside every license of SOLIDWORKS. It allows you to do a basic stress analysis on a single part. Or you maybe are familiar with the slightly more comprehensive simulation inside SOLIDWORKS Premium, which again is a stress analysis, but it would allow you to do simulation on a full assembly with more types of loads and some more controls on the mesh and things like that. And when we typically talk about stress analysis, especially what you're able to use inside SOLIDWORKS Premium, we specifically mean something called linear static analysis. So even though it covers many types of stress analysis, it actually is only going to be valid in specific instances, specific types of loading conditions. So of course, you're able to put in things like material properties and the loading conditions like we're talking about, forces or gravity, and you're going to get stresses in the material and displacements and strain and factor of safety out of that. But the types of loads that you're able to put in, even though they may be the vast majority of cases, are sometimes not good representations of the real world loads that are happening. And so if you look at this chart, you can tell that when we talk about linear static, which again is the type of simulation in SOLIDWORKS Premium, it really is only going to accurately simulate one of these four possible different loading conditions you're seeing. We've got a large cantilever beam, maybe it's attached, to a wall of some kind, to a building, and you got a weight on the end of it, an anvil or something, right? So if that beam was, basically just starting out in its undeformed shape, and I simply placed a big weight at the end, assuming it didn't deform too much, that would be a valid case to use the linear static analysis. Where you need to get into these areas of nonlinearity and dynamic simulation is when those loading conditions and also the results, potentially, are different than that. So what if the weight, for example, was much larger and it caused that cantilever beam to flex a large amount? Well, at a certain point, the amount of that deformation in the beam is going to be beyond what we call the linear range. There is something called the small displacements or small deformations assumption in linear static analysis, where if you go beyond that, the linear solver is not going to really give it an accurate prediction of the stresses or the displacements in that material. So beyond a certain amount of displacement, you need a nonlinear solver in order to find that answer correctly. Similarly, depending on how the weight of that anvil or weight of that object, whatever it may be, is applied, a static simulation might not be acceptable. Static, of course, refers to having the conditions relatively constant or at least applied slowly enough that the rate at which the events happen doesn't really matter. But of course, if I was going to drop this anvil on the end of the beam instead of just placing it there gently, that's going to generate some additional stresses in the material due to the inertial effects of the weight and the impact and the dampening effects inside the material. And those are going to change the results of the stress in those objects beyond just the static assumption. So of course, if I dropped a small weight on there, maybe I don't have a large displacement in the cantilever beam, so it would be still a linear problem, but it would be a dynamic problem. Or maybe I drop that weight and it's a very large weight, which means I need to not only account for the dynamic aspects of the problem, but also the large deformation of the beam itself. So as you can see, there's situations where linear static simply does not fit the bill. So how do you get those other types of simulation? Well, again, I mentioned that the basic stress analysis, which we now know is actually linear static analysis, is contained inside SOLIDWORKS Premium. So that gets you your linear static stress analysis and also motion simulation. Beyond that, we have some other simulation packages, such as Simulation Professional, which is going to add some other study types that also are typically linear in nature, although they are checking for different kinds of failure. For example, the thermal analysis is going to check for a temperature limit, or the fatigue analysis will give you an estimate of repeated loading cycles, or the frequency analysis will tell you what the natural frequencies and mode shapes of your object are. Beyond that is the highest package we have called SOLIDWORKS Simulation Premium. And that's the level of the software which is going to include these nonlinear and dynamic capabilities. So we'll go over those in a little more detail in just a moment. Also, just be aware that those tiers you're seeing on the left are finite element analysis packages. So that refers, again, mainly to stress analysis or some other type of analysis only on the solid material of your products that you're designing. We also have some other simulation tools, such as our flow simulation product, which can analyze liquid or gas flows in or around your model. We also have sustainability, which can estimate the carbon footprint and environmental impact of your designs. And also plastics, which will simulate the manufacturing process for any injection molded plastic parts. So again, these nonlinear and dynamic capabilities are contained in that Simulation Premium package, and they can basically expand the capabilities of SOLIDWORKS simulation to handle those different loading conditions and handle a lot of different types of loading conditions. And especially in the dynamic tools, we're able to simulate many different types of input and output requirements that we might need to predict failure in a variety of scenarios. One other thing I'll just mention briefly, even though we're not going into detail about it, is that Simulation Premium also enables you to use composite materials in your linear stress analysis. So if you have carbon fiber or other stack-ups that you need to simulate, you'll be able to specify all the plies of the material. how many layers there are and the thicknesses of each layer and their orientation. And that way you'll be able to get a much more accurate picture of the stress inside those composite materials. And you'll even be able to predict things like delamination. So let's focus in a little bit more now on what exactly you can do in the nonlinear and dynamic studies. And let's first look at nonlinear and how that compares to static analysis. So the first thing that you'll need to know is that there are multiple kinds of nonlinearity inside this, this type of a study that might exist compared to a static analysis. The main one, which I already mentioned, is what we call large deformation or geometric nonlinearity. And that essentially is any situation where the part that you've designed or the assembly that you've designed is being deformed beyond that small displacements range, that small displacements assumption. And it's not necessarily a fixed number or anything like that, but a good guideline is if you can imagine your product being deformed in the real world with whatever loads you've decided to put on it, if you are likely to be able to see clearly that part deforming, it's probably beyond the small displacement range. So if you can see it with the naked eye without examining it closely or using a pair of calipers, it's probably a nonlinear problem. In addition to that, any study where you need to account for nonlinear material behavior, such as the post-yielding behavior of ductile metals or inherently nonlinear materials like rubbers and plastics, or things that perhaps stretch at different rates depending on how much you have stressed them, those also will require a nonlinear analysis. And as you're able to see there in the screenshot below, that means, again, we can handle things that deform a lot, and that we'll also be able to see response plots of how much they are deforming as we apply the loads. In addition to the geometrical and the material nonlinearity, the last one is that in the nonlinear static analysis, we're also able to change the loading conditions over the course of the analysis that we run. So that means we're able to do any problem where we might want to apply a load and then take the load off. For example, if we're trying to do a metal forming analysis or check what the permanently deformed shape of a part is, if it's been yielded. We're also able to do complex contact analysis. For example, gear tooth interactions as they're turning, or clip engagement, or anything where components might be bumping or sliding together where the shape of them or the positions of them are changing as the loads are applied. So let's look at a basic example of this inside SOLIDWORKS. Here's an example. We have a pretty simple part, which in this case is an electrical connector that you might find on a typical circuit board, for example. So of course, it's a relatively simple part, and it's a single body in this case. But if we needed to, we could of course run a nonlinear stress analysis on an assembly as well. You're not simply limited to one part. So let's look at the differences between linear and nonlinear on this part. Let's run it as a linear static analysis first. For those of you that aren't familiar, you can, of course, go right into the SOLIDWORKS Simulation add-in that would be enabled here, and the tab that's in your command manager to access the commands that you need. Then we can create a new study by going right to this drop-down from the study advisor. Of course, you could also use the study advisor, which is a wizard-like interface, if you're just starting out with the software and you need some guidance. So on the left-hand side, these are all the study types that are available to us. And where you see it says static at the top under the type menu is where you're actually selecting a linear static study. And again, that's what you would have in just SOLIDWORKS Premium. So let's create our new study called linear static. And of course, we get our study tree on the left-hand side of the screen, which is basically going to split the feature tree in half. And we would need to go down this list and apply things like our materials and our loading conditions. And so, for example, this connector, which is just, again, one body, might be made out of 6061. So we could either pick a predefined material from the library, Or we might want to pick a custom material if our properties are slightly different. So let's use this 6061 alloy that's been user defined. Of course, then we can also restrain the model. How is it going to be held in place with the rest of the components that it's going to be connected to? And then how is it going to be loaded? And again, there's a lot of different options for that. But in this case, we might want to fix this thing at one of the attachment points, for example. And then we might want to just put a force on another area of the model, perhaps on the bottom right side, going downwards. And then, of course, finally, we can mesh and run this simulation. So I can right-click and say Create Mesh. And the various meshing tools inside SOLIDWORKS Simulation will be the same whether you're using a linear static study or a nonlinear. So the good news is that you won't have to relearn or reinvent the wheel if you've already used some of the more basic tools here. So, of course, we can use our different meshing options we have, like the curvature-based mesher, which will automatically adjust the mesh size to map to the geometry better. And then, of course, we can run this analysis and see some results. So let's switch back here to the one I've already done. And actually, let's go ahead and run it just so you can get an idea of how quickly this linear study will solve. So in fact, it solves so quickly, you may not even been able to see the progress bar of the solver appear. And that, of course, is the reason why we use the linear study in a lot of cases, because it's faster. But as we'll see in a minute here, it's simply not going to give us the right answer in some other cases. If we look at this stress plot, like we can get in any kind of stress analysis and simulation, we're able to see, of course, the deformed shape of the part and what the stresses are reaching. And if you look at the plot on the right-hand side of the screen, this is showing von Mises stress in PSI, pounds per square inch. And the maximum value that it's showing on the screen here is about 15,000. Now, the yield stress is also shown on the screen. And that's shown with the red arrow down below. And as you can see, the highest stress in the model is far beyond the yield strength of the material. Now, when you're running a linear static study, because we can't account for those nonlinear material properties, we don't have the nonlinear material model that's needed, those stresses above the yield are actually not going to be reliable numbers. In fact, if I go into the color plot here for this stress plot, and under the color options, choose this option that says specify color for values above yield limit, it's very easy to see that this study is predicting the part will yield almost over the entire geometry. So almost the entire part it's saying has been permanently deformed and basically is going to be failing. Now that may not seem quite right, or even if you don't know, you can tell that just having a stress value that's more than 10 times above the yield probably doesn't sound quite right, because that most likely is also above the ultimate strength of the material, meaning that the part would probably be completely breaking in pieces at this point, with cracks or fractures all over it. And that, again, this load value that we put in is only 5 newtons, and that may not seem quite right. And if you had that suspicion, you're actually correct. And the number one way that you can tell that this linear study probably is not giving the right answer is that if I animate this and look at the deformed shape of the part, I can clearly see the deformed shape, even though this deformation scale is set to 1. And again, as I told you before, a good guideline is that if the deformation is clearly visible to the naked eye, it's probably beyond what's acceptable for this linear region. So let's run the same analysis as a nonlinear study now. When you're setting up a nonlinear analysis, there really isn't much you need to do beyond the same conditions that we created in the linear study. In fact, you can frequently drag and drop those conditions from one study to another, which is a nice time saver. The only thing that's different in the nonlinear study is that since the loading conditions like forces or gravity can be applied slowly with changing conditions, we're able to go into the definition of these loads and actually plot a curve of how those loads vary with time. can see here that in this particular case, what we're doing is punching in a few data points to simulate that this same 5 Newton load is being applied slowly from 0 up to that full value. And then it's going to be removed at the same rate, so that after about 1 second here, we will have put the load on all the way and then taken it off, which is going to allow us to see if the part has yielded, what is its final shape, even after we've taken the load off, because it will have some permanent deformation in there. So let's go ahead and run this simulation, which of course is going to take longer now because nonlinear analysis is more complex. So we can see that the study is currently being solved. In this case, even though it is a relatively simple part, it'll take probably about 30 seconds or so. And then we get our results. So let's look at the stress plot this time. Here we're seeing that the maximum stress is about 1.85 times 10 to the 4th psi. So we are almost an order of magnitude lower than the maximum stress that the linear study predicted. We're also showing, again, that option where any of the areas of the part above yield are shown in gray. And whereas before in the linear results, it predicted that almost the entire part would be yielding, the nonlinear study does not show that behavior. The nonlinear study shows that really only this small stem part of the connector to where the fixture was applied is going to be yielding. So now we know from running a nonlinear analysis that the stresses predicted in the linear study were not accurate. And more importantly, if we were trying to figure out whether this connector merely was permanently bent or if it was actually going to break apart by comparing these results to the ultimate stress of the material, we would now have a reliable number that we could actually check with some certainty. So the nonlinear study helps you predict not just if yielding will happen, but what something will look like if it does yield. We can, of course, also look at the displacement plots here. And this is showing that the maximum displacement is about 0.103 inches, whereas the linear study predicted a maximum displacement of about 0.03 inches. So again, that was not an accurate result. Of course, we can also view what the strain of the model is and see what this permanent strain looks like after the load's been completely removed, which in this case is at the end of this 1 second time period. Finally, we can also plot this response, which in this case is showing the displacement of a point kind of near the bottom right of this part where the load was applied. And we can see how the load, of course, even though it's constantly applied up to this 0.5 seconds, is causing the displacement to start out and then rapidly increase. And this point where the slope of the line changes is where the part would have been yielded. And of course, if you are familiar with metals like 61 alloy, they tend to bend much more easily after you yield them. Then, of course, at this point, you can see the displacement reaches a maximum and it starts to go back down again. And that would be where the load reached its maximum value and we started to remove it. But of course, you can tell that at the end of the simulation, we still had some permanent displacement here, which is showing us that the part has in fact been permanently deformed. So its shape has been changed. Again, other examples of the nonlinear study could be used for situations where you have the connector that perhaps is rubbing against a wire and you want to see perhaps how the contact stresses develop over time, or if you expect the wire to be permanently kinked or bent, depending on how it's moved. All of those things with changing loading conditions, nonlinear materials, and larger displacements can be analyzed with the nonlinear study. Okay, let's switch gears now and talk about the dynamic versus static dichotomy. So we already talked about how nonlinear versus linear refers mainly to whether or not the loads change and whether or not the model behavior is going to have larger displacements and certain nonlinear material properties about them. Well, linear dynamic analysis instead is going to use a different approach to solve the problem, where the solution and the assumptions in the analysis will still be linear. So we're back to assuming that the displacement in the model is not going to be large, and also that the materials will just behave linearly. In other words, we're only able to check up to the yield of the material. But because this is going to be a dynamic analysis now, we're going to be able to account for loading conditions that change rapidly. For example, shock loads or vibrations. And we'll be able to account for the other factors in those loads, like the inertial and the damping effects of them, which can add to the stress values that we see. Now, linear dynamic analysis in Simulation Premium is not simply one kind of a study. It actually encompasses several different study types. And each of these has slightly different inputs that you would put into the software and slightly different results that you would get out of it. For example, time history analysis is used to simulate one shock or loading event where, for example, you want to see the vibrations in the product over time. How long does it take that product to stop vibrating? Or how much will it vibrate from that single impact or shock load? And of course, what are the stresses? Some of the other studies we have, though, are used not just to simulate one single event, but sort of a family of events. For example, the harmonic analysis is used to simulate a frequency sweep where you might be applying a harmonic, constant vibrating load that's oscillating back and forth over a large spectrum of frequencies. So for example, that could be an electric motor on a frame that is rotating at different RPMs and maybe has an imbalance to it that's causing different magnitudes of vibration depending on how fast the motor is spinning. Random vibration also is similar to that, where you're going to analyze the product over a frequency range, but random vibration is used when the exact nature of those individual vibration events may not specifically be known. For example, if you're trying to design an electronics package that is mounted to a vehicle that could be vibrating at unknown magnitudes or rates, or perhaps designing something to seismic safety limits where you are expecting earthquakes or other seismic activity to happen, but you don't necessarily know how big they will be or how frequently they are going to be occurring. And so the random vibration study will give you some results that show what the maximum stresses or displacements will be within a certain percentage of the time. It's more of a statistical analysis. Let's look at a little more depth at one of these types of studies, the time history analysis, which again is going to allow you to simulate the response of the model to loading conditions over time. Now, this might seem a little bit similar to what we just did with the nonlinear analysis, because we did have a curve showing how the force was changing over time in the nonlinear study. But the difference is that with that nonlinear study, we couldn't account for any of the vibrating or inertial effects that would be important if this load was actually applied very quickly. You might remember that we were saying the force we had was applied slowly over about 1 second. If we wanted to simulate that that was a shock load, though, that happened maybe in 1/10 of a second, that's nonlinear analysis, which was still a static analysis, would also not give us the correct answer. So the time history analysis would be required if we expected any kind of vibration effects from applying this load so quickly. So again, this is a type of simulation you might need to do in mil-spec situations where you have a product that is mounted to a vehicle that is going to likely encounter some sort of a shock or collision. And we're still going to put in material definitions and fixtures and restraints, but we'll also now be able to input as loading conditions, not just forces or displacements or pressures, but we'll actually be able to input accelerations or velocities as well as a load. So we'll be able to define that our product perhaps is mounted to a vehicle or is in a test sled that is being impacted into a wall and is experiencing a certain number of g-forces. And of course, out of that, we'll get stresses and displacements over time and response graphs, similar to what we just saw in the nonlinear study. Now, the inputs for the time history analysis often will look rather different. You might have half-sine or sawtooth or triangle inputs for the loading conditions, whether that's, again, g-forces and how they might be changing over time, often you'll see that you have a large spike in the increase in the g-forces, and then they'll go back to zero, and you'll have a longer period where they stay at zero, where we're simulating that the vehicle's already come to rest, for example, and we just want to see what the vibrating response of the model is, which is what you're getting in the graph down below. So those are showing the displacements of some different points on the model over time as they vibrate back and forth. Let's look at how we would set up one of those types of analyses. Here we've got a small circuit board that's mounted on a tray, which again might be in some sort of rack, maybe some server equipment or some optical equipment that's on a vehicle perhaps. And you can see we've got some different types of studies down here. Let's focus on the time history study, and then we'll also just briefly mention the frequency analysis beforehand. I showed you prior to this an image of the different packages we have, and you saw that the frequency study is part of SOLIDWORKS Simulation Professional. Now, the frequency analysis is something that's actually done as part of any of these more advanced dynamic analyses. And really what these linear dynamic studies are doing is an extension of the frequency study. So the frequency study is only going to show us what the natural frequencies or modal shapes of a product are. For example, this circuit board, after we run the frequency analysis, is showing a natural frequency at about 166 hertz. But this study is not able to tell us what the stresses or displacements in the model will be because we haven't defined what the actual load is yet. However, this information is going to be used via what we call modal analysis to predict in those more advanced study types what the real stresses and displacements actually will be once we define a specific input load. So the frequency analysis gives us an idea of what directions the product might vibrate in and what frequencies it might get excited at. And the linear dynamic studies will tell us the actual results, the displacements and the stresses. So for the time history analysis, let's go ahead and look at the setup here. Of course, this is a slightly more complex model now than the electrical connector. So we have a PCB with all of the components you'd expect on it, like capacitors and transistors. And the materials have all been applied in SOLIDWORKS, so they're already specified for us inside SOLIDWORKS simulation. And we even have a couple parts, like for example, this 1060 alloy sheet metal shield that are going to be meshed automatically with the correct element type, which is in this case, shell elements, which are great for thin components like this. Of course, that is the same behavior as you'd see in any kind of stress analysis in SOLIDWORKS simulation. Now we've decided to fix this model by selecting some bolt holes in the sheet metal tray that the board sits on. So that's where it would be mounted to, the rack, for example. And of course, we have our mesh with some mesh controls to get a little better accuracy in some certain areas. What you may notice is that we don't have any kind of forces applied as loading conditions on this model. Instead, under external loads, we have something called a base excitation. Now, if I wanted to, I could put forces or pressures on. But more frequently, as I mentioned, this type of study is used to simulate an impact of some kind, which probably means that the object that this product is mounted to, in this case the rack, is probably experiencing some accelerations or velocities that are known to us. For example, if it was a test of some sort of crash, the test fixture, the sled, would probably be propelled at certain accelerations into a wall. So we're able to define what that motion looks like. We're able to define how the accelerations or the displacements or the velocities change over time. In this case, again, I have this variation with time curve that I'm entering. And what I'm saying in this case is that this study is going to run only for about 1/10 of a second. You can see in the X column there, that's time. We're going from 0 to 0.1. And what we're saying is that over the first 100th or so of a second, we're going to be ramping up the G-forces to about 50 Gs. And then all of a sudden, it's going to drop down to 0 Gs. So that basically is the impact. We're, of course, simulating that if this is mounted kind of vertically against the vehicle, that it's going to be rapidly slowing down when it impacts something. And then, of course, the G-forces will be stopped. And we'll be able to see for the last 1/10 or so of a second what happens to the board. How much does it vibrate? how long does it take for those vibrations to stop. We, of course, could specify other loads too. We could specify a shock load or an impact load as a force or a pressure, which also would have a similar curve applied to it, where we would directly input the magnitude, a certain number of pounds of force is applied, like a hammer strike maybe, and how quickly it's applied, which of course is just dependent on how fast you swing the hammer. The other thing that's important to define in these types of dynamic studies is something called damping. And again, damping is another one of these, basically these factors that the dynamic studies will account for, but the static studies will not. And the damping in this case is specified as what we call a modal damping ratio. And that's basically going to simulate how much energy is lost from this model, from the product, as it vibrates and responds to the dynamic loads. If you didn't have any damping specified, you would basically see that the object is going to continue vibrating or oscillating at the same rate forever, like a ball bouncing up at the same height every time for infinity, which of course is not realistic. We all know that there's no such thing as perpetual motion. So the damping ratios should be specified to get an accurate picture of how long it will take for the energy from the loading to dissipate. And of course, we'll be able to see how long it vibrates for. So there's a lot of guidelines for what kind of damping ratio you should use. There's things like quality factors that you often will find in your mil spec. In this case, we specified 0.02, or roughly 2%. And that's going to be the damping ratio for all the different modes that might get excited. And again, those modes are something that the frequency analysis would find. You'd be able to specify different damping ratios at different modes if you needed to. And again, this damping is accounting for everything from the resistance of friction from joints that have been bolted or welded together, perhaps. It's accounting for resistance from the air, and basically anything else that might dampen out the motion. So of course we can run this analysis as well, and this one would take a little bit longer to run. Again, it has to solve several steps in the analysis where you're basically looking at what happens over the different time periods, similar to the nonlinear analysis. And this particular one would take, let's see here, a couple minutes to run. And so let's look at a stress plot here. So the first thing we're able to see is that the stress in this case at 0.011 seconds is it's a little over 4,000 psi in a few areas. And the maximum was actually a lot higher than that in one of the attachments for the transformer. And we're able to animate this plot, whether it's stress or displacement, to actually see from the impact itself how the model would respond. Now, in this case, we're doing this at a deformed scale that's been exaggerated so that we can see it more clearly. But as you can tell, the first part of the impact where we're looking at this, of course, very slow motion, you're seeing the board kind of flex, and then it snaps back and vibrates a little bit. That would be when the vehicle or whatever it is has collided into the wall and then stops. And after, of course, it stopped, you'll get sort of that whiplash effect where it snaps back and vibrates. And because of the damping ratio we put in, we can see that the vibrations slow down rather quickly and damp out. So already we have been able to estimate what the maximum stresses from this impact are. And of course, we can compare that to the yield in the materials and figure out, what our factor of safety is or if something is likely to break. But more importantly, those values would be more accurate than if we just assumed that we had a constant 50 Gs, for example, on this object, which is the only way you could do this as a linear static simulation. And those results would be wildly different. We also, of course, could look at the displacement over time. So again, this analysis is showing us that at the peak of the impact, the displacement gets up to about 0.02 inches. So of course, it's still very small, which is why we're viewing this as an exaggerated scale. But that's also why it's acceptable in this case to use a linear study. In this case, it's a linear dynamic study to do the analysis. Finally, we're able to look at response plots that show us exactly how the different parts on the model are responding over time. And this is showing, of course, that at the initial impact, we have the most displacement, and then we have some oscillations over time as we see the board vibrate back and forth until the vibrations get damped out all the way up until the end time there. So again, the time history study can give you a more accurate picture of exactly what the maximum loads, and maximum stresses in the model will be from those loads, but also we'll be able to show you what the response looks like and how long it takes for those loads to damp out and the model to go back to normal. Finally, there's another category that you may have seen in that first chart with the cantilever beam and the anvil, and that combines both of these different avenues of expanded situations that we've been talking about. It combines nonlinearity instead of linearity, and it combines dynamics instead of statics. So it's called nonlinear dynamic analysis. Nonlinear dynamic analysis is the most realistic form of analysis that we have in SOLIDWORKS simulation. And so it's going to combine not only the nonlinear capabilities of being able to handle large displacements in an object and nonlinear materials like elastics and rubbers and things, and also the post-yielding behavior of metals, but it will also be able to handle those dynamic loading conditions where you might have vibrations from a quickly applied load or any other type of simulation where the impact or speeds or accelerations of the objects as they're moving around are important. So this could simulate, for example, the circuit board that we just looked at, but also be able to handle large displacements in the board and would be able to show us if any of the components on the board not only yielded, but if they were permanently bent, what they actually would look like. And would also even be able to show us if any of the parts on the board were colliding together as they deformed. For example, in the image on the bottom of the screen here, this is a small power supply enclosure, and the connectors have been deformed a lot from an impact where they are banging into each other. In the linear dynamic analysis, we can't handle those types of complex contact, but in the nonlinear dynamic analysis, it is possible. Just be aware that the nonlinear dynamic analysis does use a different solving approach than linear dynamics, so it is going to be more computationally intensive. But in many cases, it's the only way to run the type of a simulation you're trying to get. And if you're in any way familiar with the drop test study in SOLIDWORKS Simulation Professional, that actually is a type of nonlinear dynamic analysis, although it has been streamlined greatly to only account for one type of a problem, which is dropping a product onto a flat surface. So if you think you have a situation where your product needs to undergo something like drop test, but it's a little different, for example, you want to simulate another object impacting your product instead, or maybe a projectile of some kind, or again, pieces of the product permanently deforming or contacting with each other, then nonlinear dynamic analysis is what you'd want to look at. Of course, if you have any interest in these different study types, we have a lot of customers that have been using them, so we can get you a reference for a customer in your industry. Just be sure to contact either your account manager or myself by email, and we can get you that information. Also, just so you're aware of it, we do have a continuing Webinar Wednesday schedule. It's going to proceed after this week. Starting next week, June 18th, we're going to have another e-learning in the morning at 11 a.m. and another eDemo in the afternoon. The e-learning will be on simulation again, and it will be a quick lesson on meshing 101. I'll give you some tips and tricks there if you maybe have gone through the training but are looking for a little more instruction. Maybe you haven't gone through the training yet. Also, the eDemo will be on the SOLIDWORKS Enterprise PDM. And then the following week on June 25th, we'll have an e-learning on SOLIDWORKS Electrical, how to create custom symbols in that product. And then also a demo on SOLIDWORKS Composer. It's going to clarify some questions that people have about that product and how it can help you create documentation and instructions for anything that you're designing. Once again, just want to say thanks for attending and your time today. Hopefully it was informative for you and that you now have a much better idea of when you need to account for nonlinearity and dynamics in your simulations and whether or not you need the capabilities in SOLIDWORKS Simulation Premium. I'm going to stick around for a few minutes here and try to answer some questions. Otherwise, Of course, feel free to email me at damontia@hawkridgesys.com, or you can always contact the support team by web or the phone numbers, which is also on the website. We had a question from Rafi. Rafi was wondering what version of SOLIDWORKS I was using. That was SOLIDWORKS 2014, the latest version of SOLIDWORKS, which has been out since October last year. There are several enhancements to SOLIDWORKS 2014. Primarily, there's a couple additions to the way that we can handle some connectors and some enhanced result viewing options. If you go to the Hawkridge Systems website, hawkridgesys.com, you can go to events, and there's a list of previously recorded webinars. And we did do a webinar several months back on the new features in SOLIDWORKS Simulation for 2014. So I would encourage you to check them out. Also, this webinar will be available. We're going to post a link to the presentation that I used. You'll get that in the outgoing email that's going to follow up with the presentation. And you also will be able to see this presentation recorded later and posted on our website under events. Brad is asking if it's possible to define a nonlinear spring force versus displacement instead of time. Brad, not specifically. We actually have had that as a request before. We do have spring connector in our stress analysis that you might be aware of. We don't currently have the ability to do nonlinear springs. We have that in as an enhancement request to SOLIDWORKS, which they are working on. In the meantime, the workaround is that you can model a component with beam elements, which are basically just long and slender bars. And then you'll be able to apply any properties, any material properties you want to that, which you can use to mimic a nonlinear spring. Angel's asking, in regards to mechanical components like helical springs, does the software simulate damping behavior based on material properties or on mechanical components? So, Angel, that's a good question. There's actually another method to enter the damping. You can define damping coefficients inside the material definitions in the material library, which means that in any situation, if you use that material on that part, it will use the same damping coefficient. So you can do that. However, it's not always recommended because in a lot of situations, you may have a part that is made out of the same material as something else, but it may not actually dampen out the same way because of how it's, the shape of the part or how it's attached or what environment it's in. We do also have a different way to handle damping called Rayleigh damping in the nonlinear dynamics study, which does have a material coefficient in there, as well as another term that you can input. So there are several options, and that's kind of the thing we go over in the training class to help you figure out which approach you need to use. Melkor asks, is there a limitation in the number of nodes or number of parts that you can bring into a fatigue simulation? Good question. Actually, there isn't a limitation built into the software on fatigue or any other kind of stress analysis. The limitation is going to be on the hardware that you have in your computer and how fine you're trying to make the mesh. So as an example, on my computer, which is an HP laptop, if you want to take a look at my system properties here, I have about 8 gigs of RAM. And with 8 gigs of RAM, I should be able to handle up to several million degrees of freedom, probably at least 10 million degrees of freedom, which would typically mean, a couple million nodes probably. And the simulations I was just running were probably more like 50,000 degrees of freedom. So I could do models that were, many, many times more complex, of course, even than the circuit board. But it is a function of the computer hardware you've got. So if you need to do bigger problems, just add more RAM. You can add as much RAM as you want, and simulation will use whatever is on your computer. It'll use 32 gigs of RAM if you have it. It'll also use all of your CPU cores, however many you have. Milker's also asking, can SolidWorks simulation take advantage of NVIDIA, Tesla, or other HPC technologies without resorting to the cloud? If you're referring to graphics card processing, GPU processing, currently we don't support that in SolidWorks simulation. It's only going to use your CPU, but that is something, of course, that they've looked at for the future, but no plans to add that functionality as of right now. So if you're looking to increase the performance of your simulations and make them run faster, the main thing that will affect that is the CPU, both the clock speed and how many cores that you have inside the CPU. I know that it's been tested and people have benchmarked simulation to use up to, I think, 12 cores and maybe even higher than that. But it'll use as many as you have that Windows is recognizing. You can even do dual CPU systems. I know there are a few systems, a few motherboards that have dual CPU sockets for Xeon processors, the server processors, and I think AMD Opteron processors too. So you're only going to be limited by whatever hardware is out there. Okay, if you have any more questions, go ahead and plug those into the chat panel. Otherwise, looks like we are wrapped up. Again, I just want to thank you one more time for attending today, and I hope it was useful to you. Please make sure to check the schedule for Webinar Wednesday in the future, and of course, contact us if you have any questions. All right, thanks again. Everyone have a good afternoon.